Hi, I'm Colin, and I'm a software engineer at LangChain. In this video, I'm really excited to talk about a new feature we just launched for deep agents and decode called dynamic subagents. Your agent can already hand off work to subagents. Dynamic subagents take this one step further and let it spawn and coordinate those subagents programmatically by writing code. This gives your agent the ability to more reliably decompose and break down large tasks into smaller parallel work items where it might otherwise struggle. Let me show you what this looks like. This is Decode, our terminal coding agent built using a deep agent. I've got a request ready to send, and one thing to know up front is that the workflow keyword can be used to signal to your agent that you want it to write code and spawn subagents to help do the job. The request that I've got queued up here says, run a workflow that fans out 15 subagents and have each one write a different breakfast themed haiku. When those finish, I want the agent just to pick the one it thinks the best and share it with me. You can see the agent picked up my request, and you can see that it knows that I wanted it to fan out the 15 subagents in parallel. So a couple things to watch here. This panel that just popped up is the dynamic subagents view. This tracks every subagent that's running, what each one is working on, and how long it's taking. Each phase that you see on the left side of the UI represents one instance where the agent is fanning out a batch of subagents in parallel to handle one part of the task. The agent is doing all of this by writing code to programmatically spawn and coordinate all of these subagents. This is a really simple example, but dynamic subagents are a really powerful feature that agents can use for decomposing large tasks at scale. So that's a look at dynamic subagents, but let's dive in deeper. So why do we need this? I think it helps to start with what we already have. Deep agents already has subagents, and they're great. The main thing that they give you is context isolation. Each subagent runs in its own context window. It does a piece of the work, and it hands back just the results. So the main agent's context can stay clean. That already exists, and it's still true here. If subagents already do that, though, then why dynamic subagents? Well, here's the gap. Normally, the main agent orchestrates its subagents itself. It calls the subagent tool, which is the task tool in deep agents. It looks at what comes back, and then it decides what to call next, and that process repeats until it thinks it's completed the work that you asked it to do. That's totally fine for a handful of calls, but all of that orchestration is happening in the agent's own reasoning and in its own context. The moment that the task gets really big or repetitive, this starts to become unreliable. You'll see that the agent will start to lose track. It'll start to skip things. It decides that it's done early. Sometimes it takes a really bad trajectory. So here's a great example of how to think about this. Let's say that you want to summarize every page in a book, and let's say that you have one subagent per page. With plain tool calling, you're relying on the main agent to call the subagent tool a few hundred times in a row, and you're asking it to do all of that without losing the plot. With dynamic subagents, this just becomes a case where the agent just needs to write a loop. It just writes a few lines of code that spins up one subagent per page and collects the results. So the orchestration effectively moves out of the agent's head and into code. And that's really the whole idea. When the orchestration logic is easier or more reliable to express in code than to have the agent generate it each turn, the agent has the ability to write code. The payoff here is really reliability at scale, as well as complex multi-step workflows. So what do you actually get by moving orchestration into code? Well, for us, two things really stand out. The first one is reliable coverage at scale. A loop runs for every item. So the agent gets through, say, all 500 files, not just the 75 files that it felt like doing. Completeness then stops depending on the agent's discretion, and it also stops becoming a prompt engineering problem that you have to consistently try to tune to get the right behavior. The second is real control flow. Things like loops and branching, retries, and running things in parallel. All the stuff that's really awkward and error prone when the agent has to do it turn by turn in its head, that now just becomes a few lines of code that the agent has to write. And that's it. So how does the agent run the code? That's our code interpreter middleware. Just a lightweight in-memory sandbox, and it gives the agent access to an eval tool. And so this allows the agent to write a block of code, give it to the eval tool, the runtime runs it, and only the final result comes back to the agent. which is part of how the context stays so clean. The important part for us with dynamic subagents is that the middleware also exposes a task global by default. I mentioned the task tool, and the task global is just a programmatic version of that tool that the agent can use in code to programmatically spawn subagents. So spawning a subagent from inside that code is just a programmatic function call. The agent just has to call a wait task with a description, a subagent type, and optionally, it can also pass a dynamically generated response schema so that the result from the task global comes back typed. That typed result is really important because it's what lets the agent loop or branch on what its subagent returns, allowing for more complex multi-step workflows all in code. There's really just two things that you need to use this. The first is just attach the code interpreter middleware. If you're building your own deep agent with the Deep Agents SDK, all you need to do is import the code interpreter middleware and pass it in when you're creating your agent. And that's it. The agent will now have the ability to write code and use the task global to programmatically spawn subagents. This also ships by default in decode, which is what you saw in the demo. So the second piece is, how do you trigger it? Well, you trigger it using the workflow keyword. Once the middleware is attached to your deep agent, the agent can write code to orchestrate subagents, but it won't always decide to do that on its own. Putting workflow in your request, though, is the signal that you want it to. So, for example, review every file in this PR may or may not fan out, but something like run a workflow to review every file in this PR explicitly tells the agent that you want it to write the orchestration code. So I want you to keep this in mind because this is exactly how you steer every one of these patterns that I'm about to show you in the coming slides. Here are the 6 patterns that are most common. These patterns naturally emerge based on the shape of the task that the agent is solving. And like I said, you steer it with how you phrase the workflow request. These patterns were originally coined by Anthropic in their work on dynamic workflows, but we see these same shapes show up in dynamic subagents. I'll walk you through all 6, and for each one, I'll give you the kind of task it fits, the request that gets you there, and we'll also take a look at a real LangSmith trace so you can see it happen. Pattern 1 is classify and act. This one's the simplest, and this one's all about routing. You use this when your inputs are all jumbled together, and different kinds need different handling via different subagent types. You would reach for this when you're doing work like triaging support tickets or sorting error logs or routing user feedback. The agent reads each one of the items, it decides what type the item is, and it hands it to the subagent that's right for that type. To steer towards this, phrase the workflow requests around the types. Something like run a workflow to take these 200 tickets, figure out what each one is, and handle it the right way. Whatever the right way is for your specific type and task. That figure out what each one is really what makes it classify first instead of treating every item as the same. Let's jump into the LangSmith trace for this to see what it looks like. First, you can see the request I said. I said run a workflow to triage the support tickets in a specific JSON-L file that I set up. I explicitly asked the agent to classify each as a bug, a feature request, or a question, and I also gave it specific handling instructions for each one of those types. What's interesting here is that you'll see that the classify part of the classify and act pattern took place over a read file call and an eval call. And that's interesting because we found that the agent could work the best when it could naturally decompose tasks in whatever way it saw fit. So in this case, the agent used its read file tool to take a look at the JSON-L file that I pointed it at. It took a look at each ticket in the JSON-L file, and then it used its eval tool, which is it using the code interpreter middleware to classify each of those tickets. And you can see that it created an array of tickets, put every one of the tickets in that array, and then it classified each one as a bug, a feature request, or a question. And so the act part of the classify and act pattern is in the second eval call that we see. What you'll notice is that the agent then sorted each ticket as a bug ticket, a little more detail in the body, and then it's each of the feature tickets, and it sorted each of the question tickets. So it created a separate array for each ticket type, gave a little bit more detail based on the classification that it did earlier. Going a little bit further down, you can actually see where it's using the task global and fanning out to different subagents. So you can see that it fanned out in parallel all of the bugs to the bug investigator subagent type. So what's really interesting is the agent has the ability to target specific subagent types for different tasks that it's solving. So all of the bugs went to the bug investigator subagent type. All of the features went to the feature analyst subagent type. And all of the question tickets went to support responder subagent type. Another thing to note here is that you see a description. Each description is essentially just the system prompt that's being passed to the specific subagent. The last thing I'll point out here is that you can see that we have a dynamically generated response schema based on the request that I sent and the handling that I wanted for each ticket classification type. So the agent is able to dynamically generate those response schemas, and that gives it a way to know that it's going to have a specific output from the task global call. So let's take a look at what this actually looked like. Here's the full triage summary with all 10 tickets. You can see the bug classifications, the feature request classifications, and the question classifications. And you can also see that the agent took specific action that I asked it to take in the request for each of those specific ticket types. So that's classify and act. The next pattern is fan out and synthesize. This one's all about coverage. This is where you have the same job, you have many items, and you want to run all of these in parallel and have them merged into one final answer as your output. You would reach for this for work like per file code reviews, maybe analyzing a batch of documents, or performing the same check across a whole fleet of services. You steer towards this pattern with words like every and all, plus a single combined output. So an example of a request that I might send here is review every file in this PR and give me one summary of the problems. The every word forces the coverage, and one summary here is what adds the synthesize step on the end. So let's take a look at the trace. You can see the request that I sent. I said, run a security review workflow over the utility code in source utils. I said, cover every file in that directory. Don't skip any. Then give me a single prioritized report of the top risks. So that single prioritized report is the synthesize step that I asked for. Here's the eval call where the agent is writing code. You can see that it organized each file in the source utils directory into a files array. And then you can see where it used promise.all to fan out to each subagent type that it's targeting. In this case, it's just targeting one. It's targeting a security reviewer. You can see that every security reviewer subagent is getting a small variation of this description, the system prompt, that's just different based on the file type. And then you can also see the response schema that was dynamically generated by the agent. You can see here reviews. This final line here is the final return type that actually ends up going back into the main agent's context. So let's take a look at the fan out. So you can see each of these fanned out. And you'll also notice that when it returned this reviews, we have one more eval call here where the agent took reviews here and it performed a flatten and it ranked all. So it did a flat map and then it was able to rank all of these based on severity. So we have critical, high, medium, and low. And so that completes the fan out and the synthesize. And so we should be able to see the final report that was generated. And here it is. So the agent gave me the full prioritized security report across all 5 files. It found 48 total, 8 critical, 18 high, 14 medium, and 8 low. And you can see that it gave me the information I asked for in my request. The third pattern is adversarial verification. This one's all about precision. You would use this when a wrong answer is expensive and you'd rather miss a few things than report something false. You'd want to reach for this when you're performing work around things like security audits or compliance checks or high stakes reviews where you want high confidence. Typically, this pattern is going to run in 2 passes. The first pass is what goes wide. It's the one that produces the candidates. The second is where we send those candidates to independent verifiers. And then only the findings that survive a final majority vote are the ones that get reported back to you. To steer towards this pattern, ask for confidence explicitly. As an example, you might say something like, run a workflow to find the security issues, but only report the ones that you're sure about and double check each one before you do. That double check is what adds the second adversarial pass. I said, run a security audit workflow over the utility code in the source utils directory. Cover every file in that directory and look for vulnerabilities. And then the key here is I said, independently verify each one before it goes in the report. I doubled down on this and I said, I only want real confirmed issues, so no maybe or theoretical risks. And then I asked it for a short report of the confirmed findings at the end. So let's take a look at that. So here's the first eval call we see. You can see the files array that was set up again based on the files in the source utils directory. But interestingly here, we see that the agent actually commented and said, hey, here's stage 1 where I want you to audit all files in parallel. So it fanned out. This is the candidate pass where it's generating the candidates. And in this case, we're targeting the auditor subagent type. Here's our description, which is again the system prompt. And again, it's only just being differentiated based on the file type. And again, we see our dynamically generated response schema. If you go a little bit further down, you can see where it's using what it knows is going to be included in that response schema to write code. Additionally, you can see all findings here. So we have an all findings variable, and this is what's being returned to the main agent's context. So it's going to see this before taking the next step, which should be the verification pass. So let's take a look at that. Okay, we see our second eval call here. And what I really want to point out here is you'll notice all findings here. Variables that are stored are persistent across eval calls. So in eval call 1, the agent created this all findings variable, and then it was able to both return the data from that, because that was the final return of that eval, to the agent's main context, but it was actually also able to incorporate that in code in the second eval call, which is again a really powerful thing because it allows the agent to be iterative. Also, because it was able to use the response schema, it's able to know what fields are going to be included on all findings. So you can see for each finding, it knows it's going to have a type, a line, evidence, explanation, etc. So it gives the agent the ability to orchestrate some of these multi-step, more complicated workflows. So again, you can see that in this case, we're doing the verification pass and we're targeting the verifier subagent type. You can see the system prompt that's sent to each verifier. And you can see the dynamically generated response schema where we're looking at confirmed or a reason. So let's take a look at the final output of this. So you can see here that we actually ended up confirming 22 of the 26 with 4 being rejected. And you can see the reason for each rejection here. And you can see the fan out as well. So let's go up and look at our final output from the agent. And here it is. You can see that it reported 22 confirmed findings, 4 were rejected. And here's the security audit report generated from adversarial verification. So a really cool pattern used for high confidence. Pattern 4 is generate and filter. This is when I would say we're moving more into quality as a focus. In this pattern, you'll take several subagents, have them independently take a shot at the same type of problem, and then the agent scores them and keeps the strongest one. You'd use this for more open-ended work where one attempt usually isn't the best attempt. Reach for this for architectural proposals, refactoring strategies, or content variations. To steer towards this pattern, ask for several and then ask to pick. So, for example, you might say, run a workflow to give me different approaches to this refactor, and then tell me which one is the best and why. A few different approaches is what creates the diversity, and which one is the best is what adds the filter. So let's jump into the trace for this one. In this case, you can see my request. I'm focusing on a rate limiter here. I'm saying, hey, this is the wrong design for our scale, and I've been trying to do one-shots, but they just keep coming back mediocre. I asked the agent to run a workflow that explores a few different redesigns. I asked for token bucket, sliding window, leaky bucket, and GCRA. I asked it to write each one as a concise design sketch and to write it under its own file in a candidates directory. Then I asked it to weigh them on a few different criteria and recommend the strongest with a clear rationale for why it wins. So let's take a look at that. So this first eval should be our generate. And we see that the agent took those designs for the rate limiter that I asked for and it expanded on them. So it targeted the candidates directory with a file. And here's token bucket, and here's the prompt and the design that it's asking the subagent to generate. Going a little bit further down, we can see the sliding window counter and the file that it's targeting for that. We can see the leaky bucket and the file that it's targeting for that. And the last one is GCRA. So here's all of my designs. And you can see that at the bottom, this is where we're doing the fan out using the task global. And in this case, we're targeting the systems designer subagent. Now, what's interesting about this one compared to every other example that I've showed you is that we don't have a response schema here. And the reason that we don't have a response schema for this one is because we told the agent to write all of these to a file. So that's one option that you can pick as well if it fits your use case better. So that should be the generate step. Now let's go look for the filter. One thing to notice as I'm scrolling through all this, we talked about context a lot. You can see just how long each of these sub-agent calls go for and how many tool calls they're making as they're trying to generate the rate limiter design. This is all about context isolation. So this is where sub-agents are really powerful because all of this is staying out of the main agent's context window. We see a few eval calls, but what's really interesting here is we can see that decision, the filter here, is actually happening as a regular task tool call. And this goes back to what I mentioned about iterative and not forcing the agent a specific way of tackling these problems. So in this case, it handled the generate step with an eval call where it out to the systems designer. But once the designs were done, then it handed it using a regular task tool call to a design evaluator. So this is where it's actually selecting the best of the designs, and we can go back up and look at what the final output of that was. We can see the files that were produced. We had token bucket, the sliding window, the leaky bucket, and GCRA. And here's our scoring matrix, and the winner was GCRA. Tournament is pattern 5. Tournament is generate and filter's competitive cousin. This is for when best is more subjective and hard to score directly. Instead of rating everything at once, the variants go head to head and a judge subagent compares them in pairs, just like you would think of any other tournament. The winners advance, rounds run until one is left standing, and style selection, picking a tone, which of these implementations feel best is the criteria that we're judging on. To steer towards this, frame it as a competition. Run a workflow to draft several versions of this headline and pick the strongest by comparing them against each other is an example of a request that I might send. That comparing them against each other is really what turns this into a bracket instead of a single scored list. So let's hop into the trace for this one. You can see in this case, I have a create orders handler. I said it's messy and I want the best possible rewrite. I said run a workflow that produces several candidate rewrites with different priorities. Readability, robustness, performance, and minimal diff. I wanted it again to save each one to its own file under the candidates directory. And then I explicitly said, compare them head to head in a tournament, advancing winners until one stands out. The first part of our tournament here, here's our candidates that the agent generated. And you can see that it is fanning out, in this case, to the writer subagent. Again, because we're writing the files, we don't have a dynamically generated response schema. So we've now generated our candidates. The next eval we should see should be the first part of the tournament. And here we go. We found another eval call and aptly named round 1. So round 1, you can see that we're fanning out to a judge and we're comparing candidate A and candidate B. So this is readability versus robustness. It also includes the original here. And then you can see a second judge call where we're putting head-to-head performance versus minimal diff. And you can see that we have an output for this that goes back into the main agent's context, which is the output of round 1. So we should see round 2 further down. And we do. And you can see that this is the final. So again, we're fanning out to the judge subagent type. And in this case, you can see that robustness and performance both moved on from round 1. And now we're comparing those head to head to figure out who the actual winner is going to be. So let's go up and take a look at the final result. We can see robustness won. We can actually see the tournament bracket breakdown here where we had versus robustness, performance versus minimal diff. Robustness and performance moved on, and robustness was the ultimate winner. The final pattern is loop until done. This one's all about exhaustiveness. The agent runs a pass, it dedupes against what it already found, runs another, and it really only stops when a pass turns up nothing new. Use this for exhaustive searches, dead codes detection, and dependency audits. To steer towards this, make completeness the stopping condition. For example, you might say something like, run a workflow to find all the dead code in this repo, and don't stop until a full pass turns up nothing new. The all and the don't stop until are what creates the loop and also gives the agent an exit point. So let's take a look at this trace. You can see the request I sent. Run a thorough security review workflow over the code and source utils. Work in passes. Each pass looks only for issues earlier passes missed, and you keep going only while new issues keep turning up. In this case, I capped it at 3 passes, but you could let this run until nothing new shows up. So here's our first call. And you can see pass 1. It's explicitly saying, hey, this is a broad sweep, all 5 files in parallel, general security issues. So this is the first attempt at surfacing issues. And you can see we're summarizing what pass 1 already found. So this is the deduplication step. And then we're fanning out, again, using what pass 1 already found. And we're passing that in as context to pass 2 so that we can try to surface new issues. And this should be the final pass 3. So you can see it's building all combined. It's building a combined list of all the findings so far. again, for deduplication. And here's the third pass, which is saying an ultra targeted, give each scanner the full already found list. So those are all three passes, and we can see what the final output here looked like. Perfect. You can see it says all three passes done. Here are the consolidated findings. So it went through 3 rounds. It kept deduplicating what the previous rounds found, and it ran 3 times. But again, you could let this run exhaustive until it completely finishes. So those are all 6 patterns, and that's dynamic subagents. Dynamic subagents add reliable programmatic orchestration on top, so your agent can take a big job, break it into a lot of small ones, and actually finish them reliably at scale. 2 places to get started. Attach the code interpreter middleware to your deep agent, or you can just reach for decode where it's on by default. We're really excited about dynamic subagents, and we can't wait for you to try it out. I'm Colin. Thanks for watching.